Hi everyone, and thank you for the introduction. So yes, the work I'm going to present today is SmartTokens, embedding motion and grip sensing in small tangible objects. So while tangible user interfaces have come a long way, interactive token-based tangible interfaces still remain fairly unexplored. By token-based tangible interfaces, I mean interfaces based on collections of an early example was the Lego wall prototype developed by Molenbeek in 1985, where each token was actually a Lego brick and was representing time periods in a schedule. And this one is a modernized version by Vitamin. So tokens are used a lot in our everyday life, like, for example, coins or like poker chips. But very few tangible interfaces actually use tokens. Take Bishop's smart balancing machine, for example. It is considered as one of the founding concepts of tangible user interfaces and used tokens to represent audio messages. Yet, it has only inspired very few actual tangible user interfaces systems. So how could such a system look like nowadays? Well, this contemporary version would be dealing with notifications. Existing notification systems typically use subtle visual or auditory cues, but these can still be quite distracting. With token dispensers as physical notification machines, users can be quite creative in the way they set notification levels. This dispenser, for example, has been moved far away, and a foam board has been placed to muffle the sound of falling tokens. Meanwhile, this louder dispenser is for important messages. Not only can the user use the physical tokens as reminder of pending notifications, but they can also interact with them. And for example, the user can touch the token to pick up the message. While a simple contact displays only the sender and the title, pinching it shows the entire message. Grasping and shaking the token marks the message as important, and dropping it back into the dispensers unassigns it. So why isn't there such a thing? Well, mainly because it's quite hard to build due to the lack of appropriate technology. Such technology would need to satisfy several requirements. The first one, it needs to be able to detect users' manipulations. The system would also need to be able to know what the user is doing, even if the objects are hidden in his or her hand. Several objects should fit in a hand, and for this, the form factor has to be compact. The system should also be able to be installed easily and shouldn't restrict the interaction space to the dedicated location. So looking at what already exists, many technologies are possible for tracking tangibles. These fall roughly into two categories. The first one consists in using an external sensing system. These can use, for example, cameras or RFID tags or magnetic sensors to track tangibles' position and orientation. So external sensing is able to sense users' manipulations, but occlusion often prevents sensing during in-hand manipulations. Multiple objects can be tracked, and compact objects are supported, as any passive physical object can be augmented with markers. Yet, a setup is needed for the sensing, and these systems have a limited range and need to be used on specific and specialized surfaces. So the second approach aims at embedding sensing within the objects. For instance, systems like Curlybot or Topobo are able to record manipulations to replay them later on. Taylor's graspables are using capacitive touch sensors distributed on their inner surfaces, coupled with accelerometers to recognize grip and orientation to change function in consequence. And finally, Merrill and colleagues introduced SIF tables and later SIF-TO cubes. Each block has a screen, motion, and proximity sensors, and can be assembled together as building blocks to create larger interactive devices. So here, manipulation within the hand no longer poses a problem, but using multiple objects at once is supported since each object is sensing itself. But internal sensing tends to make objects more complex more costly, and more bulky. Since tangible objects do not rely on external sensing equipment, they are easier to use and can be operated in many diverse physical environments. So it seems that using internal sensing is more appropriate for building token-based tangible interfaces. But current devices are either too complex or too bulky. So the challenge here is to keep all the advantages of internal sensing while trying to reduce the form factor. So to fill this gap, we propose smart tokens. Smart tokens are small tangible objects capable of sensing grip and motion and sending input events wirelessly. Smart tokens broaden the scope of what is possible in tangible user interfaces, as they are simple and cost-effective, but still smart enough to be used as handles for digital information. Smart tokens allow to make generic, scalable, and affordable user interfaces. They embed custom electronics, including touch and motion sensors, as well as wireless communication functionalities. With 6 different touch sensors distributed on their inner surface, smart tokens are able to distinguish multiple types of grips, such as pushing, pinching, holding, or grasping. Smart tokens also embed accelerometers to detect and measure movement. Each smart token can then recognize basic motions, such as folds, moves, or shakes. So with these 2 input channels, each smart token can now know whether it is touched or not, and also if it's moving or still. So the cross product of these 2 input channels yields to 4 different states, each representing a situation in which a smart token can be during a manipulation. Inspired by Buxton's 3-state model, we combine these states together to create a state machine. Each transition from one state to another represents an input event that can be used to trigger a function. So take a basic interaction, for example, starting with a still smart token. One touching it makes it change state, creating a touch event. So from this state, giving some motion to the smart token makes it change state and create a move event. Let's have a look at a few real-life examples. So in this very first case, this is a very simple manipulation of a smart token. So at the beginning, the token is left alone without contact. But as soon as the user touches the token, it changes state and sends a touch event. Grasping and moving the token leads to a move event. And as stopped and released, the token moves back to its initial state, and it indicates it with several events. Smart tokens are joining a network to communicate information. This not only allows wireless communication, but also flexibility in the system, as smart tokens can jump in and out the network seamlessly. Each is given an ID, which allows the system to keep track of the current tokens in the network, and information is attached to each smart token. So information then remains, information attached to the smart tokens remain persistent as they come back into the network. And coming back to our state machine, we can see that multiplying the amount of smart tokens makes no difference. We can easily turn the state machine into a Petri net, and we can see that each smart token is sending its own information independently from the others. So to sum up, smart tokens are tangible objects capable of sensing users' manipulations, even in hand. Several smart tokens can be manipulated at the same time, thanks to their small form factor, and the system is easy to use and doesn't restrict to a specific location. To use smart tokens, and assuming that you have the provided framework, implementing this notification is relatively effortless and accessible to anyone with basic prototyping and programming skills. So after making the machine, for example, one only needs to use a bit of coding to listen to incoming notifications, and using our API, Smart Tokens event can be used to modify these notifications. But this is just an example, and one can easily imagine using smart tokens with different form factors to create, for example, interactive board games or physical data storytelling. So if you have any other idea for application, or if you want to improve the technology, smart tokens are completely open source, and all the material to use smart tokens or to make them is available on GitHub. And voila, thank you for your attention, and I will now be happy to take your questions.
Thank you, Mathieu. Any questions? I have a question for you. So I realize this is UIST, I realize this is a systems paper, but could you comment a little bit on any user studies you might have done, or to what extent smart tokens impact the usability of these kinds of token-based systems?
So I would say it's more a technology enabler system in the way that we provide a platform, like a self-contained platform to prototype and experiment with new types of, with token-based tangible interfaces in the way that you have these tokens that are able to sense the manipulation. You can use half of them, part of them, I don't know, depends, but yeah, to create new types of, different types of interfaces. And then for the evaluation part, for example, I don't know, you could imagine how, first looking at how people would react to actually active tangibles like that, in the way that they're active but without output, so people are not able to distinguish actually what is happening. So looking at how participants would react to the input, to simple input on the tokens, and then how well the group is distinguished, for example, or what type of gesture we could implement with them, or yeah, things like that.
Yeah, I imagine, because you know, with these token-based systems, it can be hard to deduce what they are when they happen, because you have to do something with them to show it on a screen. Or, and if you now start moving them and using that as a kind of a gesture, then it's kind of critical. You know what it is before you do that, because you might be deleting information that you don't want to delete.
Yeah. But you can easily imagine just adding very simple output channels, for example, like a simple LED or a vibrator motor inside, so you could have something feedback as the users are actually using the token. So a gesture would be validated by a I don't know, vibration or something like that, for example.
Okay, any questions?
Hi, Victor from TU Berlin. Thank you for your work. I just have a short question. How much such a token would be? Do you have any sense of how much the production would be?
I have an idea about the material you need for it, as so it's just super simple 3D printing with the cheapest Ultimaker thing and a bit of electronics to make and a few chips. I didn't count my work in it, but just the making it is I don't know, something $15 to $20 approximately.
Okay, thank you.
Hi, Rong Hao from National Taiwan University. And since this is an active token technology, I wonder that is there any challenge about wireless charging? Yeah, if I combine a wireless charging into the physical constraint, is there any possible design? Have you considered that?
Yeah, definitely. So one thing that is in my future work, basically, and I've thought about is using the touch antennas that are distributed around the surface as receiving antennas for wireless charging, basically. And when the token would be, for example, in the dispenser, you would have an active inductive charger in the thing. So as soon as you put the token in its container or something like that, it would charge back, and you would basically, it would be completely transparent for you in a way that you wouldn't have to worry about the charging anymore. It's just when you put it back into the container, it would charge. So yes, definitely. I couldn't look into it yet, but I'm planning to, yes.